Welcome to this episode of the Structural Engineering Channel, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives. In this episode, Rachel and I will be talking with Michael McDonagh, Vice President and Senior Technical Principal at WSP. What was really cool about this episode is we got to learn about ultra high performance concrete, or UHPC for short. I thought it was really cool as a structural engineer in the building industry. It's not really used there, but I got to see the benefits of it on how strong it can get. I believe it's twice as strong as the concrete that I've ever used, but it also has some steel fibers in it. So he gets into explanations about that, which I thought were really interesting, and how it's being used in the US right now and how it will be used for future applications. I'm your co-host, Matt McCardle.
And I'm your co-host, Rachel Holland. Now let's jump into the conversation of the week.
Hey, Michael, so nice to have you on the show. Can you tell us about your journey in civil engineering, how you got here, and how did you end up as a specialist in bridge design using ultra-high performance concrete?
Sure. Hello, Matt. Thanks for having me on. Perhaps a lot to unpack in that question, but so let's see. My career, I graduated from Penn State University in 1997, grew up in Pennsylvania, then I decided I wanted to try out the West Coast. So I moved out to Seattle, took a job there. And one of my early jobs was on an architectural bridge. I was specializing in bridge design. There was this unique job that had an architect involved, and I got really fascinated with that and really kind of started seeking out how to make bridges look better. That was kind of a little side passion. And I even thought about maybe going back to school for a master's in architecture. Because a lot of bridge design is just, you pull the standard specs out of the DOT handbook and, copy, paste, repeat. And a lot of the bridges are very plain looking. So I was hoping to make an impact in that regard. And I had a few inroads in that. But a side interest of mine was the French language. I'd studied that in high school, a little bit in college. And an opportunity came up for me to relocate to France, actually to move to France. And I quit my job in the US and took a job with a French engineering company. And aside from the French aspect, the part of the appeal was that this company I was working for specialized in sort of landmark, signature, high-end projects. And I thought, hey, this is a chance for me to combine my interest in aesthetics, with my design skills or bridge design skills. So I took that job, had a big adventure. I spent about 5 years in France. And the reason this is all relevant is because that was where I first encountered ultra-high performance concrete. Europe generally has been ahead of the United States in the adoption of UHPC, ultra-high performance concrete. And Europe was predominantly using it in architectural applications. As we may get into, the properties of UHPC allow you to make really thin elements and highly detailed things. And Europe, and France in particular, has done a lot of cool things with that. So I started designing with it. Unfortunately, none of my UHPC designs that I did in France actually got built. Either the projects never moved forward or the UHPC got value engineered out of the jobs, because it can be it is an expensive material, but it depends how you use it. But in any event, so I had a pretty good introduction to UHPC when I was working in France. And at the time, I was not envisioning that becoming a special part of my career, but I was intrigued by the innovative aspect of it and some unique things you could do with it. So completely unrelated to any of that, I decided I was done living in France. I decided to move back to the United States and moved back to the East Coast, close to where I grew up. And took a job with the company that now is WSP. At the time, it was Parsons Brinckerhoff. And as pure coincidence, the project I was being hired for was the redecking of the Pulaski Skyway. Pulaski Skyway is a 3.5 mile long elevated viaduct, runs from basically Jersey City to Newark, New Jersey. If anybody was a fan of The Sopranos. I am told, forgive me, I've never watched it, but I'm told this Pulaski Skyway features large in that series, especially, I think even the opening credits, you can see this big black elevated truss in the background. In any event, the project was to redeck the entire Skyway. And just prior to my starting on the job and with the new company, the decision had already been made that they were going to use precast concrete deck panels with ultra high performance concrete to connect them, which had only been done a handful of times. And this was by all means the would be, and still is to this day, the largest use of UHPC by volume on a single project. So it was actually kind of funny for me because starting out on that project, in Europe, they tend to refer to UHPC as UHPFRC. They like to reinforce, no pun intended, the fiber reinforced aspect of it, because UHPC has, by definition, has fibers in it. So anyway, the first few days, my U.S. colleagues are talking UHPC, I'm talking UHPFRC, and then we're debating about, what's happening with the fibers until we realize, okay, we're all talking the same thing. And then I had project meetings, and I'm meeting guys from the UHPC company supplier who used to be head of the French division. Now they're head of the North American division, and we're looking at each other like, wait a minute, what are you doing here? You're supposed to be over in France. But anyway, that project, as I said, to this day is still the largest single use of UHPC. So that kind of became a big part of my resume in terms of, experience with regards to UHPC. So, and right around that same time, the Federal Highway Administration in their Turner Fairbanks Highway Research Lab, unbeknownst to me, they had been studying UHPC very closely since the early 2000s. And they were really just getting ready to, in many ways, go public with design guidance specific to connections at this point. And they did that, published the first one in 2014. And then they started up this program. Well, I should say they participated in this program that had already been created called Everyday Counts. And this is a program that the Federal Highways operates to promote what they consider to be proven and innovative strategies to, reduce maintenance, shorten construction time, basically to reduce traffic congestion and overall construction, because every day counts. So they want to promote these technologies they feel are proven and are valuable, but are not well adopted yet. So they go and promote it, and it goes in 2-year cycles. And so they had chosen to promote UHPC for connections. And typically they hire a consultant to help them in this promotion. And so my company, applied or sent in a proposal for the contract. And, our resume, having done Pulaski Skyway plus my prior experience in Europe, was very strong, and we got that contract. So me and a colleague of mine then we were working hand in hand with Federal Highways. We were touring the country, giving 8-hour workshops to state DOTs on working with UHPC, helping Federal Highways update their design guidance, writing white papers, a whole bunch of stuff. And that was really sort of the entry point for me into the greater world of UHPC within the United States. And then one thing kept leading to another, where, the head of the UHPC division at the Turner Fairbanks Highway Research Lab was also the chair of the new International Interactive Symposium on UHPC, which was first held in 2016. So he invited me to join the organizing committee, which I did. And then I met more people, and it just kind of kept on snowballing from there. And then plus with my knowledge, I was looking for opportunities to incorporate UHPC in projects that I was involved in as well. So that kept snowballing. And at one point, for about a 2-year period from early 2021 to late 2022, I actually left WSP to pursue an opportunity with a commercial UHPC supplier. It was a unique opportunity, and I was excited about the opportunity to sort of see the other side of UHPC, the manufacturer working with contractors and quality control and all that. And then I came back to WSP after that. So, and then I also got involved in another Everyday Counts phase where Federal Highways decided they were going to promote UHPC for bridge deck overlays. And for that, I was involved in authoring or co-authoring 4 or 5 different federal highways publications. There's at least 2 that haven't been published yet. But yeah, like I said, everything just kind of has kept on snowballing. And now I would say on any given day, 3/4 to sometimes 100% of what I'm doing is directly related to UHPC. Whether that'll be, continue that way, I don't know, but it certainly is a big part of what I'm doing.
I loved hearing that just trajectory of your career, and I will have to go back and I've definitely watched all of The Sopranos, but I'll have to go back and check that opening credit to see.
I should watch it one of these days, at least just one episode, so I know what I'm talking about.
It's
but I've heard about it so many times.
It's a great show. I also really liked that, like, you took that adventure and moved to Europe for multiple years. That's very cool. I think that when you're starting out in this career, you never really know, like, what will lie ahead, and I think your story kind of is just very much so proof of that, right? Like, it's just like you get into one little thing and it leads to something else, and it leads to something else. Also just curious, because you did step away to go to the manufacturing side of it. You said, like, the construction side of it. Like, I would love to pick your brain on, like, being an engineer, and then, like, the pros and cons that you felt, as opposed to being more on, like, the design side of things. But
both of those decisions were difficult to make. Moving to France, leaving the design world to go work for a supplier. I think what made me make the jump each time was, if I didn't do it, I would always wonder what would it have been like, and I might regret having not done it. So I said, well, let's find out. That was kind of what guided me, I guess, or pushed me to make the leap.
Yeah. What about also just, like, bringing it back, like, down a little bit for, like, people that maybe are not familiar with the UHPC, right? Is that it right?
Yes.
Okay. The UHPC. Can you just describe what it actually is, and how is it different from just traditional concrete?
Yeah. So traditional concrete, it tends to be a mix of gravel or coarse aggregate, sands, cement. I think those 3 ingredients alone can make concrete. And there's other things that are sometimes used, silica fume and other additives. In terms of the ingredients, the 2 obvious differences is UHPC has no coarse aggregate. The largest aggregate, if you can use that term, is a fine sand. And in addition, the other obvious difference is the inclusion of steel fibers. And they're not the typical steel fibers that you would use to make fiber reinforced concrete. These fibers are typically just a 1/2 inch long, straight, and they're made from drawn wire, so they're circular in cross section with a diameter of 0.2 millimeters. So a little hazardous to work with, to be honest, because a bunch of little needles you have to be careful with. So those are, like, the obvious differences. UHPC has a lot more cement, which is one of the things that helps give it very high compressive strength. So if I move on to material properties, the latest definition out of federal highways is that UHPC should have a minimum compressive strength of 17,500 PSI, I believe. Until about a year or 2 ago, federal highways said the minimum should be 21,700 PSI. And if anybody listening to this speaks metric, they may recognize that 21.7 KSI is 150 megapascals, 17 point something is 120 megapascals. And Europe and Canada have defined UHPC as kind of falling in 1 or 2 categories of strength. And after some early concerns that, if the strength isn't high enough, it could just be a juiced up concrete and not UHPC, federal highways finally said, they can live with a 120 megapascal limit, or 17.5 KSI roughly. But I'm diverging there. It's a very high compressive strength, which in many cases is not in itself not a terribly attractive property. Now, there are some applications where it can be, but in the many ways UHPC is being used to date, the compressive strength is not terribly important. What tends to be given more importance is the fact that its durability is, I think you could call it extreme. So if anybody's familiar with a rapid chloride penetration test, it's a way of measuring the permeability of concrete. And, if liquid permeates your concrete, water, of course, but if you're in a coastal zone or an area that uses road salts, you're going to have salt in that as well. And then that can hit your rebar, corrode your rebar. And that's really the cause of a lot of concrete bridge deterioration we have in the country to this day. So conventional concrete, I think if you just take an average conventional concrete, you'll have a rapid chloride penetration test result of around maybe 3,000 to 4,000 coulombs. And I know it's kind of a meaningless unit, but just think of the number, 3,000 to 4,000. What's considered to be a really, really good conventional concrete that's been designed to make it as impermeable as possible, you can get it down to about 1,000 coulombs. UHPC, by most definitions, has a maximum allowed value of 250 coulombs, and most of the commercial products on the market today will give you values around 50 coulombs.
That's a big difference.
But in many respects, it's effectively impervious. And there have been studies. There was a 21-year-long study where they took UHPC samples and other things, set them on this barge at mean tide in northern Maine, off the coast of northern Maine. The tide would come in and flood it. The tide would go out and dry it out. So you have 2 wet, dry cycles a day. You have freeze thaw in the winter and all that. After 21 years, UHPC was still looking good. They broke open the samples. The rebar looked like it was brand new, no signs of any corrosion, whereas other materials they put out there had disintegrated in some cases. And they took that data and they measured depths of chlorides and they did some extrapolation, and they found that chlorides just really didn't want to penetrate much more than a 1/4 inch. And when they extrapolated that data, using scientific principles, they found that, if you were to have, say, a bridge deck with a 2-inch concrete cover, in order for enough chlorides to penetrate to initiate corrosion of that rebar, assuming you have rebar 2 inches below the surface, it would take 400 years or more for that to happen. So it's like really amazing stuff in terms of durability. And when it cracks, because you've all these little tiny steel fibers just scattered everywhere inside the material, the cracks are ultra fine, they're dispersed, they're in many cases invisible, unless you take measures to make them visible. And they're so fine that water and chlorides have a really hard time penetrating those cracks. And it's only when you kind of stress the UHPC to its limit where will you finally start getting a single crack that's opening up wide. But if you've gotten to that point, you're talking about structural failure or imminent structural failure. So durability is its main selling point. Now, another potential, which has not been fully exploited yet, but I believe we're on the cusp of it, is to make use of that really high compressive strength to make precast UHPC girders. Because of that really high compressive strength, you can put so much more pre or post tensioning in those girders and combine that with the steel fibers giving UHPC very high shear resistance. You can make exceptionally long girders, much more so than you can do with conventional concrete. You can eliminate probably all of the shear stirrups because all the fibers in the UHPC can carry that shear by itself, and really do some amazing things. And in some cases, do it for equal or less cost than a conventional concrete girder, despite the material itself, on a volumetric basis being up to 10 times that of conventional concrete. So there's an introduction to UHPC.
That's really cool. So I had a question so it seems like the steel fibers are by definition always an ultra high performance concrete.
Yes.
And it seems like that's for shear and reducing cracks. Are there any other reasons? Does it increase tensile strength or?
Yes, it imparts significant tensile strength, and that will depend on how much fiber you put in it. Usually we're talking 2% by volume of steel fiber to about 3%. That's the typical range that's being used.
Cool.
So,
and it's just scattered in the mix. It's like part of the mix. There's no specific way in which that's laid out.
Correct. And there's some debate about that because, if you're trying to cast a long and thin member out of UHPC, if you just pour the UHPC off from one end and just let it keep on flowing to the other end, which could be 10, 20, 30 feet away, your fibers may start to align with the member just because the action flowing over that distance, which could be a good thing, could be a bad thing, right? Good thing would be, yeah, you'll get more strength, more tensile or flexible strength in that direction, but you may be sacrificing durability or what's what I'm looking for, ductility in the other direction. It may become brittle in the other direction if you don't have enough fiber. So, and that's the other thing fiber gives it is ductility. So people have made relatively thin slabs of UHPC, like 1 or 2 inches thick. I don't have numbers in my head, but I'm imagining maybe 1 or 2 inches thick over like a 10-foot span, and people are walking across it, and the thing's deflecting down like a good foot or two, but it's holding up because of all that steel fiber. So it actually acts like flexible concrete.
I think I've seen a clip of that. Some people standing on like a really thin, looks like concrete, but it's pretty flexible.
Right.
And that's why they call it ultra high performance concrete, right? Where it's a really high compressive strength, but to balance that out, they put steel fibers in it. So I think that's the main concern. If you go too high of a strength, it's going to be more brittle, but with those steel fibers in.
Yes.
Yep. That's pretty
that's
cool.
also why they call it ultra high performance concrete, not simply ultra high strength concrete.
Yeah.
Because again, the strength is oftentimes not the main point, right? It's the durability, it's the ductility, and yes, sometimes the strength, but strength isn't the focus because there's so much more to it.
Cool. Could you give us, I think you kind of mentioned some examples, but could you give maybe some project examples of where you explored different options and then, this really made sense for ultra high performance concrete and that's why you went with it?
Well, I mean, this is not so much a personal design decision, but I mean, the very first use of UHPC that really caught on was using it to connect precast concrete members. And you almost have to back up in, I'll say, recent history. Accelerated bridge construction was a pretty big buzzword, I'll say 10 to 15 years ago. It was the idea that, hey, well, obviously let's accelerate the construction to cut down on traffic disruptions, and it fits right into the Federal Highways Everyday Counts initiative. But the main way to do accelerated bridge construction is you precast as much of your bridge as you can off-site, leaving, if you're talking about bridge replacement, leaving the existing bridge operational. Then you shut the bridge down only as long as you need to set the precast pieces in place and connect them together. And that technology has been around for a while, but it was getting a lot more attention, said 10, 15 years ago. But what has been a persistent or almost a nagging problem with that method of construction is that those connections end up being the weak points all the time, because you've got great, factory quality control on your precast elements. Now you've got field cast concrete where quality tends to be a little bit lower. You don't have the same curing environments. And so what they were seeing is that these connections between these beautiful precast elements were failing or cracking really early. And at least with the conventional concrete, when you get cracks, now you're getting water and salts penetrating. And they were sort of the weak points from a durability perspective. So using UHPC, you eliminate that durability weak spot, right? Because now UHPC is more durable and stronger than what you're connecting. And then it made sense economically as well, not just from a durability or life cycle standpoint, but even from a first cost standpoint, there was an economic argument to be made, because with connecting precast elements, typically you are lap splicing your rebar. So with a conventional, say, 4,000 PSI deck concrete, if you have number 5, maybe number 6 size rebars, you're going to need, I'm not sure, but somewhere around 2 feet of lap splice length. So your connection has to be at least that big. Another unique aspect of UHPC, because of its very high strength in compression and tension, your lap splice length really only needs to be 8 times the diameter of the bar, which means, since we measure or we name our bar sizes in eighths of an inch, number 5 bar is a 5/8 inch diameter. That means you only need 5 inches to lap splice a number 5 bar. So these 2 foot, give or take, wide connections were shrunk down to 6 to 8 inches to build in some construction tolerance, which reduced the amount of concrete that you needed. It also pretty much eliminated the need to place any rebar within those connections because they're so narrow. You just had the rebar coming out of the precast elements and you were good to go. Form it up for your UHPC. So it would sped up construction, it increased durability, and you could do it for a similar cost often. So that has caught on hugely, and that's exactly what we did on the Pulaski Skyway now 10 years ago or more. Well, I guess construction started about 10 years ago. The other big use that is starting to catch on is using UHPC to overlay aging bridge decks. And again, there are other options out there, of course. Overlays are not a new thing. UHPC brings to the table, of course, its great durability. Now, PPC, polyester polymer concrete, has similar durability, or really impermeability is what I'm trying to refer to. But PPCs generally, they have a lower modulus. You don't consider them to be part of your structure. UHPC, the modulus is actually higher. It's stiffer than that of conventional concrete. And its bond strength to concrete is so strong that, to conventional concrete, that it kind of becomes composite with your deck. So you now have your deck that's composed of the original concrete plus the UHPC that you put on top, or maybe you replace part of the original concrete with the UHPC. So now you've made it super durable by cutting off ingress of new waters and salts. You made your deck stiffer. You probably made it stronger. I know in Europe, they are explicitly doing this type of intervention for the strength and not only the durability. So far in the US, we're just focusing on the durability, and strength is kind of like, oh yeah, we get that extra bonus, but we're not counting on it. But so you're getting things you can't get with other products, because most like PPCs, LMCs, they have lower moduluses, so they don't really contribute very much to the strength of the system. And there may be questions about the interface and the bond if you did try to consider it acting as a system. UHPC eliminates that. You get that super high durability. And because of that, the Delaware Memorial Bridge, this is a major suspension bridge connecting Newcastle, Delaware across the Delaware River, carrying Interstate 295, just last fall wrapped up putting a UHPC overlay on the entirety of one of their twin parallel suspension bridges, which was a huge leap forward in the size of implementation of that technology. There's about 30 projects that have done that so far, but none that rival the size of that. And it used almost as much UHPC as the Pulaski Skyway did, but not quite, but also a different application.
You've alluded to it a few times when you're talking about not needing the shear reinforcement in the girder and a couple of other things, but cost-wise, so the UHPC is more expensive than conventional concrete, right?
Yes, no question about that.
Quite a bit. Okay, so how do you justify, you talked a little bit about it with this, but how do you justify that, the higher costs?
Right. So like I said, with connections, you're using so much less material. It's quite possible that you could justify it on a first cost basis. If you were to use it as girders, as structural members, if you put some effort into really optimizing the cross-section of your girders for the properties of UHPC, and especially if you can, maybe make some longer spans out of it so you can offset some costs, like maybe you eliminate a pier, or maybe you make it a shallower girder for the same span, and maybe all this fill you had on an approach roadway to get up to grade, now you've eliminated 2 feet of fill over, several thousand feet. So you get a lot of cost offsets when using it for structural applications. But even so, if you really, really refine it in terms of your cross-sectional properties, I believe that I've done some simple comparisons. I believe you can get it down to almost parity on a first cost basis by using so much less material. Now, those won't always pencil out. And if you have an owner who is more forward-thinking and is concerned about durability, life cycle cost, things like that, if you factor in life cycle cost, you can absolutely show that over, say, a 50-year period, it is the most economical solution. Now, not every owner is willing or able to look at it from that way. Usually they're, look, I got a bucket of money to spend, and you just spend it this year. I want to get as many bridges out of it that I can. They don't care whether they last 10, 20, 30 years or 50 years. But yeah, so a lot of times you can make it work on a first cost basis, but even if you can't, if you look at it from a life cycle cost analysis viewpoint, you absolutely can show that it will be the most cost effective solution over time.
Okay, so just so I'm like clear on this then, like sometimes you can make it pencil out, but if you can't, that's when you would bring in sort of like the longevity of it and not having to do repairs as often and that durability aspect.
Yep.
And then when you do bring that part of it in though, it does pencil out.
Yes. Now I should say with a little bit of guesswork, educated guesswork, because we've only been working with UHPC in the United States for, it's 2024, 10 to 12 years. I'll give it 20 years if we throw in a couple early experimental projects. If we talk about overlays, because this is where the life cycle is kind of really important to make it pan out cost-wise. And of course, I'm thinking of the Delaware Memorial Bridge that I was involved in. We did a life cycle cost analysis to help the authority justify, to show the benefits. They were interested in it. They wanted to explore it. And the life cycle cost analysis showed, look, it is a good value for you to pursue this. But to do that, we assigned life cycles of an existing deck rehabilitated with UHPC of between 30 and 50 years, depending on how much UHPC we were putting on top. The oldest UHPC overlay that I'm aware of, at least that conforms with how we understand UHPC to be today, was built in 2004 in Switzerland. So it's 20 years old. So I can't point to a project and say, well, yeah, look at that. That one lasted 50 years. That one lasted 60 years. That data doesn't exist. But we do have that 21-year durability study that I spoke about earlier, and the test data like the rapid chloride penetration test data and other physical tests that say it's going to last a long time. But we can't really put a hard number on it. We can just take our best guess. So, but I believe we were conservative
based on some studies, based on some evidence that we're seeing. Yeah. Okay. Perfect. Yeah.
What about the sustainability aspects of it? I think the longevity aspect could contribute to that, but are there other sustainable aspects to it?
Well, yes. I mean, pretty much every how do I phrase this? Everything I sort of discussed about how can you make UHPC cost effective are really the same avenues you would go through to make it sustainable. And that is because the material is expensive, you want to use no more of it than you absolutely have to, right? And the reason I say that with regards to sustainability is UHPC has roughly twice the amount of cement as conventional concrete, on a per volume basis. And cement is a known contributor to greenhouse gas emissions, the production of cement. And so is steel. And of course, we have steel fiber inside the UHPC. So if you just look at a cubic yard of UHPC and a cubic yard of regular concrete, now, of course, regular concrete will have rebar in it, but let's just forget about the rebar for now. You would think there's no way UHPC can be sustainable because it has so much more carbon emissions in the production of it. But as I was describing, for making it cost effective, you end up using so much less material. You get so much longer service life out of it. You may be able to, in a structural application, eliminate other things like piers and less approach fill and all these other things that you can offset, that in many ways you can absolutely show that it is a sustainable material. But just like to make it cost effective, you have to use it in the right way. If you just go out and, you have a bridge with 4-foot diameter pier columns and you just say, I want to use UHPC, and now you have 4-foot diameter UHPC pier columns, it's not going to be cost effective. It's not going to be sustainable. And it would not be a wise use of UHPC. You'd be better off making a thin shell and then filling it in with conventional concrete. That way you get all the durability aspects of it, but you're not paying for highly durable UHPC in the middle of the column where you don't need it.
Interesting. Yeah. And if you compare it to like you said, if you compare it to what you're replacing, like in the example you use with like the lap splicing, it's like that much less rebar you need and stuff like that. So it's like maybe at first thought it's not sustainable, but then when you look at what the other option would be in terms of concrete as your material, it might be. Yeah. That makes sense. What about for engineers that are wanting to get into UHPC and their projects? Are there like guidelines, or is there like, what is the framework that exists? How would that look?
Yeah. So with the exception of one document, which I'll save to the end of this discussion, or the end of what I'm going to say, Federal Highways has been the main producer of UHPC guidance. Now, the Federal Highway Administration is not a code producing organization. So, until very recently, you can use their guidance, but, it's sort of off the books, if you will. It's not part of AASHTO, which is what everybody uses for bridge design. Now, most owners, trust the Federal Highway Administration, so they accept it. But, they've produced a lot of documents. They have a design guide on UHPC for connections. They have a design guide, which they simply call UHPC for bridge preservation and repair, which covers overlays with design guidance, as well as UHPC link slabs and using UHPC to repair corroded steel girder ends, which is a rather unique application for UHPC. And they have a whole bunch of white papers and other more informative documents as well. However, literally a month ago, roughly, in large part due to the efforts of the Federal Highway Administration, AASHTO just published the first guide specification for structural design with UHPC. So that's the very first recognition of UHPC by AASHTO, which I'm hoping will really open the floodgates, if you will, for much greater adoption of UHPC, especially as structural members, because that's really kind of been the one application that we have not seen a lot of use of in the United States so far. The focus has largely been on connections and overlays and other type of rehabilitation techniques. So now that there's an AASHTO guide out there, I think there's anything really stopping the industry now from starting to move ahead with structural members. And also with the support of the precast concrete industry through PCI. PCI has been studying and producing their own design guides for precast structural UHPC since maybe starting about 3 or 4 years ago, they started their efforts. I think 2022, they published a design guide. So, with the precast industry behind it, and now with an AASHTO guide spec out there, I feel like all the barriers have been removed. It's just a matter of getting owners on board, getting individual precasters on board, and making it happen. And designers, of course.
Yeah, and was that the major barrier? There wasn't a design guide for this to be more used for structural members, for structural engineers, or were there other barriers to it getting used more in the industry?
I would say that the lack of a design guide, especially for structural use, was the biggest barrier. Cost of the material is always a barrier until people understand it better and understand that they can make it cost effective. But when you tell them it's 10 times the cost per cubic yard of conventional concrete, a lot of people just say, okay, next, and they move on. They don't spend the time to look into, what it really is and how it can be used cost effectively.
So now that you have this AASHTO's, brought forward this design guide and stuff, where do you see untapped potential for UHPC? Is there like certain regions or certain types of structures or things like that you really see that it might be headed in that direction?
Well, I mean, the use of UHPC in structural members, I do believe, is untapped potential. By definition, that tends to imply new construction, right? And there's nothing wrong with that. I still think there's a lot of untapped potential in the use of UHPC for rehabilitation. One thing which I think is just around the corner, but so UHPC as a bridge deck overlay, it can, assuming all of our predictions and studies are correct, it can vastly extend the service life of existing concrete bridge decks. So in many cases, decks that you would otherwise be tearing down and replacing. So California, they have a large inventory of single or multi-cell box girder bridges, concrete box girders. So where your slab it's not only your deck to drive on, but it's also part of your structure. Like the whole box makes up what holds the bridge up. So you can't remove the top deck. You can't remove the deck without supporting the box girder from below, because it's no longer a box. So a lot of their box girder bridges are aging. The deck portions of the boxes are falling apart. So they're really looking at potentially having to replace these entire bridges, and they have a lot of them. UHPC brings the promise of being able to keep those structures in service for much, much longer, 50 years or maybe 400 years if the promises of that 21-year study pan out. So, I mean, that could be a huge cost saving. So instead of demolishing and reconstructing entire inventory of bridges, they can just go in, mill off maybe an inch or two of the top, put down UHPC, and be back in service for decades to come. So I know they're on the cusp of doing that. They even, sponsored university studies to prove that they weren't overlooking anything. I don't know when that'll happen, but I think when that does happen, that'll be a huge turning point, if you will, a milestone in the adoption of UHPC. I do work exclusively in transportation and bridge structures, but from my perspective, UHPC it's not really adopted much by any other infrastructure sectors, whether we're talking buildings, marine and ports, railroads, water conveyance, whether it's wastewater or drinking water or dams, things like that. I think UHPC has applications for all of those situations. It may go without saying now, but with all the properties we discussed, another one we didn't mention, that has very high wear resistance. So based on some information I've looked at, its resistance to wear or abrasion could be as much as 10 times that of conventional concrete. So, where you have pavements that, tire chains or studded tires are wearing ruts in the pavement, UHPC, I believe, can be a solution. Or, I'm imagining industrial ports where they've got not only massive loads wearing down all their concrete structures, but they also have, the salt air as well. To me, these are almost no-brainers for the use of UHPC, but I'm not aware that UHPC has really made inroads in there yet. And I think the only reason it has made the inroads that it has in transportation is because of the concerted promotional efforts of the Federal Highway Administration, and these other sectors haven't had that in their own respective agencies.
Yeah, it seems like it just needs to get used more and more accepted. The more use cases that we have, like the design guide, it seems like a big step. People would actually know how to design with it. And then we can see where, it feels like it has a lot of benefits, some drawbacks, but some pretty cool benefits that I feel that the structural engineering community could use, put some creativity behind it and see what stuff they can come up with.
I agree.
And Michael, final question. Do you have any final piece of advice for structural engineers, structural engineering students in their careers?
So meaning like if they're interested in getting involved in UHPC or maybe other innovative materials?
Yeah, I'd say in terms of innovative materials, UHPC seems like kind of what you're an expert in, or how you can become an expert.
I mean, I would say if you're just starting out in your career, I would encourage you to not specialize. I think you need to get a taste of everything. Try and if you're in the bridge world like me, try and design every piece of a bridge. It may not be the same project, but experience all sides of it and learn as much as you can. And certainly where there are opportunities to help out with a job using UHPC or maybe FRP, fiber reinforced polymers, or other innovative things, by all means, pursue those opportunities. But I think you want to first get a good background and just kind of observe and learn and contribute where you can. And then, as you become more established, then I think that's the time where you can start looking at specializing. I mean, looking at my own career, I never set out to specialize in UHPC. It kind of happened. So to that, I would say, where opportunities present themselves, jump on them. It may not go anywhere. Maybe I'm just thinking about some random innovative material. You may start on it, trying to focus on it and pursuing opportunities. You may find out you don't like it, or maybe it's not all it was cracked up to be. Well, you got nothing. You've lost nothing for trying, and now you can apply that energy and lessons learned into something else. So to me, I think the biggest thing is, where opportunities exist, jump on them. If you sense any, affinity towards that subject matter. To the same extent, get involved in, well, pick one, get involved in various engineering societies and maybe join one of their committees. There's a ton of committees out there between ACI, ASC, ASCE, and even sub-organizations like NSBA and I'm probably, or PCI, I'm sure I'm missing a ton of them. And they all have, subject matters committees focused on specific things that they're developing to develop guidance within their society and, for the engineering community as a whole. So, and those are great opportunities to meet experts in those fields and learn from them, whether it's just attending and learning and shaking hands or actually volunteering to help out in those committees. That will really accelerate your connections to committee members as well as your knowledge gain in whatever the subject matter may be. So yeah, starting out, I'd say, stay low for a little while, get solid in your career, get a taste of everything, and then start, getting involved in societies and committees and pursue whatever suits your fancy. And if opportunities, fall in your lap, jump on them.
Yeah, I think that's great advice to just like when an opportunity presents itself, if you're open to it, you just don't know where it's going to lead. So take advantage of an opportunity. Yeah.
Yep.
All right. Well, thank you so much, Michael, for sharing your insights and expertise with us. It was fun for me to learn about I keep getting all the acronyms mixed up, but
UHPC.
Yeah, UHPC. And thank you for being a guest on the podcast.
You're welcome. Thank you for having me.
I hope you enjoyed the episode today. We would love to hear your feedback, comments, and/or questions. To leave them, please visit structuralengineeringchannel.com. There, you'll find the summary of the key points discussed in today's episode, as well as links to any resources or websites mentioned during the episode. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. Until next time, we wish you the best in all of your structural engineering endeavors.